5.2, the definite integral. Essential question. How do I find the exact area under the curve? What are the properties of a definite integral? All right, the area under the curve is going to be defined as the limit of the sum of the areas of approximating rectangles. So here are all the rectangles, and we are going to increase the number of rectangles more and more so that we actually get the exact area. Now the definition of a definite integral, and this is what we see as a definite integral, again is the limit of the summation of all the rectangles. These are the height of the rectangles. These are the widths of the rectangles. And this x sub I is just what we call a sample point. It could be the left, it could be the mid, it could be the right. It just has to be a point in the interval. Now, when we find the exact area, what we're doing is taking a limit, and that limit, these are the requirements. That the exact area and the approximation area, you have to get to that certain number n in such that the difference between these two answers will be a very small number, epsilon, less than epsilon. Here is the integration symbol. Let's make sure we understand all the parts. B is what we call the upper limit. A is the lower limit. This is the integral sign. This part right here that shows the height of the rectangle, that's what we call the integrand. This dx is the width of the rectangle, variable of integration. And the whole symbol altogether is called the integral of f from a to b. And when you actually find an answer, you are evaluating the integral. Let's take a look at note 2. Note 2 says that the variable that you use is just holding the place of the height and the width, and it really doesn't matter whether you use x or t or even r. Okay, visually, again, this is the difference between a Riemann sum and an integral. A Riemann sum is only going to be an approximation. It's the height of the rectangles times the width of the rectangles. And the integral is actually the exact area right here. So that's the difference between them. This has error, this one does not. All right, let's take a look at what happens when a function goes above and below the x-axis. When it goes below the x-axis, these heights are now negative. And when they're negative, this accumulation of area is going to be a negative answer. And when you take the positive area rectangles and the negative area rectangles and add them all up, we call that net area. Okay, note 4. Again, this is the exact area, and these are the heights of the rectangles and the widths of the rectangles. Now, the widths don't all have to be standard size. As long as the maximum delta x is going to 0, as you increase the number of rectangles, as long as that's going to 0, then that's going to give us an integral. As long as a function is continuous and has only a finite number of jump discontinuities, the definite integral does exist. And at the end of this lesson, we'll find an example like that. All right, for our first example, let's take the limit of this summation and change it into an integral. Now right here it tells us what our interval is. It's going to be 0 to pi. And all of these are holding the place of the function. And we'll use the variable x, so this will be x cubed plus x sine of x. All of this is determining the height of the rectangle. And then the delta x, remember, is getting smaller and smaller, and that limit will change that into dx. Your turn. Try to convert all of these limits of summations into integrals. Here are the answers. All right, we can evaluate integrals not just with brute force, but with geometry. This figure is actually a quarter of a circle, and we can find the quarter of a circle with geometric formulas. Now, this area is just sum of triangles. So this triangle has a negative area, this has a positive area, and if you find the net area, you will find the actual, evaluate the integral. Go ahead and try that and compare your answers. And here are the answers. Okay, another opportunity for you to check your work. Go ahead, see if you can graph all of these and find these areas. Here are the answers. All right, let's take a look at some properties of definite integrals. Let's take a look at this definite integral from b to a. If you change the limits of integration from a to b, if you switch them, then what you're doing is you're changing the sign of the width. You're going in the opposite direction, which changes the whole sign of the whole characteristic here. That changes the sign of the answer. So this answer will be the opposite. Now, if you integrate area from A to A, in other words, you're not adding any area, then the answer is 0. So you haven't accumulated any area. Let's take a look at this example. It might be easier if we do a number example, like from 0 to 4 of 3 dx. Now, the 3 is telling me that the function is 3, so y equal to 3, and I'm going from 0 to 4, and I'm trying to find the area of this rectangle. So that answer will be 3 times 4, which is equal to 12. That's what this property is saying. This is going to be your height, and the length of the integral right here will be your width of your rectangle. So all you do is multiply these two, and that'll be the answer to the integral. The integral of the sum is the sum of the integrals, and this is not a surprise because this is a property of summations, and that's what integrals come from, is summations. Over here, if you have a constant in the integrand, then you can take it out, and this is also a property of summations, so that's why we can have it here as well. The integral of a difference is the difference of the integrals. Again, a property of summation, so it'll be a property of integrals. Let's use these properties to evaluate this. So I'm going to take this and I'm going to split it up into two integrals. I know this one, this is the constant property, so this is 4. And I'm just going to give you this answer. The answer is 1, and we could do this through brute force. That was the previous lesson. The next property tells us how we can combine integrals of the same function. So if you know the area from A to C and you know the area from C to B, then the integral from A to B will just be the sum of these two. So how would we solve this problem? We would find this. So we know from 0 to 10 is equal to 0 to 8 of this function plus 8 to 10 of this function. This is 17, this is 12, so the integral from 8 to 10 of f of x dx will be equal to 5. Your turn. Go ahead and try these problems. Here are the answers. Go ahead and use the graph to evaluate this integral. And here's the answer. Let's take a look at comparison properties. And this says that if f of x is greater than 0, in other words, this height is always greater than 0, then the answer will be greater than 0. If f of x is greater than g of x, so this height is bigger than this height, then the area accumulated here will be greater than this area over here. And this last one says that if you want to have a boundary that you want to know about this area, then take the smallest y value times the width of the interval and the largest or the maximum height and the width of the interval, and this area must be between them. Okay, and that's going to help us find this integral. This integral, we can't find the exact area, but we can see what it's between. And its maximum y value is 1, and the width is 1. And the smallest y value is 1 over e times 1 over e. So I know this integral, even though I can't evaluate it, I know that it lies between 1 over e and 1. Find the integrals of the signed area. Stop the screencast and see what you can do. And here are the answers. Integrals on a calculator, we're going to use the function integration feature on the calculator, and that's something we'll do in class. Make sure you're on me to show you how to do that. And we're going to integrate a discontinuous function. We can find this answer even though there is a discontinuous part. Then we just find the area before that discontinuity, find the area after this discontinuity, and then add them up.